v prime k, it's a vector. That's correct. I call it mu, but that's okay. It could be a v.
Oh, this.
You know, my.
Sorry.
Okay. So now the point is this: that this timing of that reaction is random, and you can actually conveniently represent it by means of something which is called a rescaled Poisson process. In other words, you can basically do the following trick. You guys, at least some of you know what the Poisson process is. This is a very simple stochastic process in which you're sort of counting the numbers of arrivals of certain events. 1, 2, 3, 4, 5, 6, 7. And the property that these arrivals have is that their timings are exponentially distributed. Okay? Turns out that it turns out, therefore, that this is a Markov process, and this process is sort of the simplest counting process that we know is called a Poisson process. And here, I can basically do a very similar type of manipulation of this much more complicated structure if I will use this rescaled Poisson process. So what exactly does it mean? It basically means that at every time after the reaction happened, I will wait for the next reaction of type K, and I will think about the rate. So I will think about the count of this reaction K as another Poisson process. But this Poisson process is rescaled. It's rescaled in the sense that its time doesn't flow on 0t now, but it basically is given by this integral, which depends on the previous state of the entire system. Okay, this is sometimes also called the density-dependent Poisson process, and this is sort of a standard stochastic version of the classical chemistry. Okay? Probabilists in the 1970s worked out most of the sort of basic stuff for these kinds of processes. They have worked out the law of large numbers, they have worked out the central limit theorem, and it turns out that these things are relevant, at least to some extent, to what I would like to do. Okay? So all right, so it turns out that there is a nice consistency result between the stochastic model and the deterministic classical chemistry. And this consistency result can be basically worked out as follows. Okay. If I assume that instead of counting molecules now, I would count or look at the concentrations of species in some large volume, call it N. So then instead of X, which was a vector of concentrations, I would actually look at the C, which is a vector of concentrations. And I would look at the number of molecules per volume. This volume is typically the physical size of the volume, say, multiplied by the Avogadro number. So that's typically a very, very large quantity in itself. Okay, so N is large. And then I can basically, I can approximate this Poisson process, this equation for the Poisson process that I showed you in the previous slide, and I'm scared to go back because I don't know if I would be able to click back to this quickly. So we just have to remember. But basically there was a description of x equals x t minus plus the vector of news, right? So this basically now can be thought of as a trajectory equation for the stochastic process. Yeah. Basically I am moving this process following that equation, updating it at random times, and then it turns out that if I follow the law of mass action, which is sort of very often a reasonable first approximation to many chemical models. It's not ideal, but, and in fact, in some circumstances it doesn't work. For instance, if you're interested in enzyme kinetics, then the law of mass action is not a good model. But in many of the models that we are interested in general, and for instance, analyzing these stochastic network methods, and I will talk about it again in a couple minutes in a little bit more detail, this law of mass action is not a bad first approximation. Okay? So for now at least I will assume that I will not worry about the fact that law of mass action sometimes is not a good thing to use, and I will just use it as an example. So basically, what happens now, if I assume that I'm under the law of mass action, that the statistical or sort of combinatorial interpretation of the law of mass action is as follows. I have some number of molecules which are floating around with this diffusion motion in the fixed volume. And what I would like to do, I would like to say, okay, this system is well mixed, meaning that in any particular portion of that volume, I roughly have the same density of molecules, which basically means that I can use straightforward combinatorics to try to figure out what is the chance that in the next instant I will have the right collection of molecules in the close proximity combine to give me the reaction. So this is basically the law of mass action. Law of mass action says the rate of the reaction is proportionate to the number of ways in which you can pick up molecules from that well-mixed system. Okay? So for instance, if it's a bimolecular reaction that only involves molecules of species A and B, then the law of mass action say that the rate in which that would happen would be some kinetic constant K times A times B, where A and B are the number of molecules at this time in the volume. Okay? So this is sort of the straightforward polynomial type of rate. So this is very good. If I make the assumption that the law of mass action is appropriate, I can basically approximate this stochastic rate that I showed you on the previous slide by a rate which looks like this, which can be written in terms of concentration function alone. It means basically it's writable in terms of just the concentrations of the volume. Okay, and then I can basically go back to the trajectory equation, I can rescale it, and then I can use a Poisson law of large numbers, which basically says that if I have appropriately large, in the appropriate scaling, I can basically say the following. If I have a Poisson process at which I've been looking for a very long time, n times u, and if I scale it by n, then this is approximately. This is sort of, again, this is a very, very simple corollary of the law of large numbers, because Poisson process is defined by these inter-arrival times which are exponential. So this is basically just the standard result related to the classical come-over of law of large numbers. Okay, so basically what happens is I have this integral equation. Once I have applied my my Poisson law of large numbers, and then I can rewrite it by differentiation, and that gives me something which is called the reaction rate equation. And in fact, this is a classical chemical kinetics equation that describes that system. Classical chemists who are not interested in small fluctuations or in small volumes in general, who are looking at these reactions which are happening very quickly to the large numbers of molecules, would simply immediately write out the equation, assuming the law of mass action. Okay. This equation is nonlinear, possibly, but under many circumstances, if I am looking, I'll say at just unimolecular reactions, so the reactions that involve only molecule A as a product, then this would be linear. Okay. But in general, these systems are relatively complicated, and they're, under most circumstances, not easily solved. Am I doing something wrong? How difficult is it to click? Yeah, but it should, it's a PDF file. I don't know. So maybe. Did we freeze this? I think so, yes. But I think I just froze the computer. So maybe I said something that was not entirely true and I decided.
So it was a PDF file?
It's a PDF.